Right, go ahead and get started here. So today first we're going to do a bit more with these shaders, just make them a little bit more interesting, because right now it just outputs like a red rectangle. So we'll add a bit more vertex data, describe that vertex data obviously, and then change our shaders just a bit. That won't take very long though, and then after that we're going to move into actually creating our wrapper library, which is basically just taking all of these parts of code, finding the commonalities between them, abstracting it out properly into like an inheritance tree, typical object-oriented stuff. Okay, so I'll just run this real quick so we can see what we have right now. Just this red or magenta or whatever other color you have, just a rectangle. Not very interesting. So what we're going to do is add a bit more data to our vertices list here. And I'm going to show off a pretty neat feature of OpenGL that hopefully will also sort of broaden your understanding of the relationship between the vertex and the fragment shaders. So I'm going to add 3 new floats to each vertex here, and that's going to be a color. So our vertices now consist of an XY pair and then an RGB pair. So this first one, it's not really important, like which colors you choose, but I just have these in this order because I think it looks nice. So we have red, green, blue, and then this last one we'll just make, let's make it white. And I'll space all my stuff out properly. All right, there we go. So the bottom left here should be red, bottom right should be green, top right should be, that should be a 1, that should be blue, and the top left should be white. So we have a bit of a problem now though that we've added all this stuff, is we're still telling OpenGL that there are only 2 floats per vertex, and that each one is the size of just those 2 floats. So what we're going to do here is enable another vertex attrib array. One, and then we will set the attributes for that. So our first one is going to remain mostly the same. Let's see if I can get the stuff showing up. Okay, so we can see here the arguments or the parameters this function takes. It takes the index, which is easy, just 0 or 1, the size, which is a bit complicated. So last time, well, it's not complicated, but I sort of glossed over it last time. So last time I just said that this was the size of each vertex, which in our simple example, it was. We just had one single grouping of data in each vertex, an XY pair, which consisted of 2 floats. But really what this is the number of elements in the current group. So this 0 group, that's going to be our position data, so the XY. So that 2 remains the same here. But then for our second one here, it's going to be 3, because we have R, G, and B. So I'll go ahead, well, I'll set that in a minute, but let's go through the rest of these. So the type isn't going to change, that's still float. Normalized, not going to change. The stride is going to change for both of these. So stride is the number of bytes in each vertex. It has nothing to do with the current group. It's not related to this number at all here, this 2. And now that we have X, Y, R, G, B, that's 5. So we're going to change this to 5 times the size of a float. This offset here will remain the same for our 0th one, because remember those come at the start of each vertex. But for our RGB pair, we're going to have to set that to something else. So once again, we're operating on index 1. The size is 3 floats per group, or sorry, 3 floats in this group, R, G, and B. The type is GL float. They are not normalized. The stride is 5 times the size of a float, because there are 5 floats in each vertex. And then the offset here, which annoyingly we have to cast to a void pointer for some reason. If you remember from the PowerPoint last time, this offset is sort of the sum of the sizes of all groups coming before it. So in this case, we just have one group coming before it. And the size of that group is going to be the number of elements in the group times the size of a float. So that's going to be 2 times the size of a float. And right now this is all really ugly and hard-coded, but just deal with it for now. That's what we're getting to today, is sort of removing all this hard-coding stuff. Okay, so once you've got that, oh, and let me zoom in a bit. I forgot to do that. Sorry about that. So yeah, once you've got that, we're going to scroll down just a bit to our vertex shader code here, and we're going to add a new line because we now have a new group, and this group is at location 1 because that's the index we specified. The type is going to be a vec3 because it's 3 floats, and I will call that iColor. Now, we have a bit of a problem here, which is that we're not going to use our color vertex data at all in our vertex shader because it has nothing to do with the position. It should have no effect on that. What we need to do is use it in our fragment shader. But our fragment shader doesn't have access to our vertex data. So what we have to do is sort of pass it down. And the way we do that is with an output variable. So above my main method here, I'll create an output vec3, and I'll call this v_color. Now this conflicts a bit, this convention conflicts a bit with what I did up here, down here in the fragment shader, which is o_color. So you can name them whatever you want, obviously, but in short, the reason I do this is that there are potentially more shader steps in between the vertex and fragment. We're not going to be doing any of them, but in that case, it gets very confusing to just name every output variable you have o_whatever, regardless of which shader it's actually coming from. So I precede it with like the first letter of the type of shader, so vertex v_. And then the fragment shader, you could do like f_color, but I don't think there are any steps after this, at least not that I've ever used. And so I just tend to go with o_color for there. But again, that's just a convention thing. You can do whatever you want. Anyways, so now that we have this output variable, we need to assign a value to it because this just declares it. It doesn't have a value yet. And so what we want to do is just pass the value from our vertex data through to the fragment shader. So we're just going to assign it directly, vColor equals iColor. So that will, remember, the vertex shader runs once for each vertex. So these, I'll scroll up a bit quickly, these 4 vec3s here will all be accounted for by this. Each of those will be assigned to iColor at some point, and then copied into vColor at some point. Okay, so now that we have this output variable from our vertex shader, we need to sort of receive it in our fragment shader. And the way we do that is very intuitive with an input variable. And very important here, they have to be the same name, and obviously the same type. So this same name thing, I believe, is what this GL-link program is responsible for down here. Because remember, we are creating 2 separate shaders, one for vertex and one for fragment, and they don't know anything about each other. So we compile them independently of each other, but then we attach them to this program. And then once you do that, you have to link the program. And I'm pretty sure what that does is say, okay, I have this variable v_color in the fragment shader. I have a variable of the same type with the same name in the vertex shader. So now that I'm the program and I have access to both of those shaders, I know that those are the same thing. So this variable is going to be exactly whatever you put in here. So now that we've done that, we don't need this hard-coded value anymore. Our output color still needs to be a vec4, so we're going to leave that constructor, but we're just going to pass in vColor as the first argument, and then give it an opacity of 1, which is the fourth argument. So I'll run this really quick, and let's see what we get. Oh, I messed something up. Ah, classic, Mr. Parentheses. There we go. So we get this weird sort of blending effect going on here. So let's take a look at the code one more time and see what's going on here. So we have these 4 color values specified. We have bottom left red, bottom right green, top right blue, top left white. I'll run one more time just to verify that. Bottom left red, bottom right green, top right blue, top left white. So that's correct. But does anyone have a guess as to what's like happening with all this weirdness in the middle? Because the vertices are correct. That's the data we've given it. But in the middle, it's like weird blending going on.
Is it combining colors?
Yes, it's doing exactly that. It's some type of interpolation process where for each pixel, it looks at the distance between that pixel and each vertex, and then does some sort of like weighted average to get the color value of that. So why this is interesting, I mean, obviously it produces a pretty neat effect, although not practical. It really shows you like the difference between the vertex shader and the fragment shader and how they interact. So I'll cover that a bit right now, just quickly. So remember, the vertex shader runs once for each vertex. We have 4 vertices. The fragment shader runs once for each pixel within a primitive. So what that means is our vertex shader will run 3 times for each triangle, right? Because each triangle has 3 vertices. And then no matter the area enclosed by that triangle, the fragment shader will be run once for each pixel within that triangle. So obviously there's a disparity there because we have 3 vertex shader calls for each triangle, but I don't know, thousands of fragment shader calls for each triangle. But we're only assigning to this variable in the vertex shader. We're only giving it 3 distinct values. So what OpenGL does is it sort of interpolates that for us. That's an automatic process. And there are like qualifiers you can put on these that will prevent that. This might not work. I don't know what I'm doing, but I've seen this flat thing before. Okay, yeah, so that just broke it. But there are ways you can prevent that if you want. But just know that the default behavior is for any numeric value passed out of the vertex shader, that value passed out of the vertex shader and received by the fragment shader, that value will be interpolated correctly for each pixel. It's not just going to be like one of the 3 values chosen at random or based on distance. It's going to be averaged. And this works for everything. It's not just color. You can do it for position. You can do it for whatever you want. Vec3, Vec4, Vec2, float. So yeah, I just think that's a cool demonstration of the difference there and the interaction between the 2 shaders. Okay, so that's all we had left to do in this sort of demo core file. So what we're going to do now is just sort of start at the top and take this apart. We're going to try and find as many commonalities between all these different things as we can. So we have vertex array, vertex buffer, index buffer, vertex buffer attributes, shaders, program, and then obviously binding all of that stuff and then finally drawing it. So the class we're going to start with, I'll go ahead and create this. Everything is going to be a header file just because that keeps it simpler. But for sort of bigger classes, it's often preferred that you just do declarations in the header file and do actual definitions in a .cpp file that includes that header file. It's just sort of a convention thing, and it can help with like just preventing circular dependencies. But because I've laid this all out beforehand, we don't need to worry about that. So everything's just going to be a header file, just to keep it simple. So this, wait, why did I name it OpenGL? That doesn't make any sense. This should be called GL object. There we go, GL object.h. And what this is going to be is, if we look at our main file here, we have lots and lots of like OpenGL IDs or pointers, like this one for our vertex array, which is passed as a pointer to GL gen vertex arrays. We have one for our vertex buffer, one for our index buffer, one for each shader, one for our program. So most of this stuff needs some sort of like ID or pointer that is given to it by OpenGL. Another thing they all need is, as we covered last time, binding is the most important part of OpenGL, because you can do all the crazy setup in the world you want, but if you don't bind it, it's not going to use it. So we should have a bind function for everything. And then also might as well throw in an unbind. That one I don't know if we're going to use. We're definitely not going to use that extensively, but it's very easy and can help if you're like debugging stuff. So yeah, let's go back to GL object here. This is going to be a class. And let's sort of stub out, well, first, let's just create the variable. So it's going to have a single variable, the ID. And this will be assigned in different ways, depending on what the object actually is. So for example, our buffers here will be passed as a pointer to one of these glgen buffer functions. Our vertex fragment shaders and our program will be assigned like as to the return value of whatever. So there's not a way to generalize that. That's going to have to be done in the constructor of each of these classes. But we can store that common data here. Oh, it's saying no uint. So the reason for this is that this is just like a standalone file. It's not included in anything yet, and I haven't included anything in it. So I'll just go ahead and include that in our all.h. Like that. And you can see that's resolved it. And the reason this works is that I'm including it after core.h. And you can see up here, core.h is where uint is defined. So if I were to move this up before core.h, it'll probably give me the same error here. Oh, maybe not. I guess I can figure that out. But either way, I'm just going to add these to the list as in the order that we create them. Okay, so typically this is like the default layout for a class. So you'll have like the public stuff, you'll have your constructors, however you spell that, blah, blah, blah. You'll have your methods, and then you might have some public fields depending on what it is, but generally in a class, most of your data fields are going to be private. However, and we could do this, but in our case, because like all of the rest of our classes are going to inherit from this, it'll be a lot easier to write that code. Well, not easier, but it'll be a lot less typing if instead of having to define, you know, like uint, get ID, and set ID, all of that stuff, we just make this protected. So this protected, you may have seen if you work in Java, they are not at all the same thing. So public and private work in C++ just like they do in Java, I'm pretty sure. Public is, anything that's public is accessible to anything that has access to the class at all. Anything that's private is only accessible within the class itself. But anything that's protected in C++, this is different in Java, in C++, anything that's protected is accessible by name in the class itself and any of its child classes. So that's exactly what we want, because we don't want this accessible to the outside world, because then they could just set the ID to some weird thing and mess it up completely. But for ease of writing our code, we can make it accessible by name to our child classes. So I'll make that protected, and we'll see this many times. So now we're going to write the constructor. If it's important. I think I'm just going to have to write this, and then I'll explain why I do this in a minute. So yeah, we have this default constructor here that doesn't take in a value. I'll just set it to 0 at first. And I'll talk about that in a minute. This is a short class, so we'll get to the next one pretty quickly. Then the next thing I'm going to do, and we're going to see this a lot, like in every single class we write, is this pattern here, where I have, if you remember those copy and move constructors from my vec2 class here, how one of them takes in a const reference, the other takes in a an L value reference, or sorry, an R value reference. We're going to have that same thing. But we're not going to define them. We're going to do something a little weird, which is delete them. You assign them to delete. So this is sort of weird syntax, but basically the reason we have to do this is that if we don't specify these, C++, the compiler will generate, it'll automatically generate a copy constructor and a move constructor for us. And we don't want that. The reason we don't want that is because, at least me, you know, like I started learning to program in Java and JavaScript, which is very different from C++ in some ways, especially when it comes to assignment and like how you pass variables and all of that stuff, which in C++ you have direct control over, and we want direct control over. And so if you just sort of slip into your old ways of writing code as you would in Java, it's very, very easy to accidentally invoke one of these automatically generated constructors, and it won't do at all what you think it does. But if we delete them here, we're explicitly telling the compiler, hey, don't create one. This doesn't exist. I'm never going to use it. And when we do that, if we, accidentally assign something a certain way that we don't mean to, the compiler will yell at us. It'll say, you're trying to access a function that doesn't exist. And then we can say, okay, great. And then depending on if we want to do that, we can either go back and like write a proper move or copy constructor, or we can say, thanks, compiler. I didn't mean to do that. I'll change the way I wrote that. So we're going to do that for both the copy constructor, which is the const reference there, and the move constructor, which is that R value reference there. Now we have the Destructor, which is also not something that exists in Java. The syntax for this is the little tilde, and then the name of the class. It doesn't take any parameters. And what this does is it's called whenever the object is destroyed. So if you have a pointer to this object and you say like delete that pointer, this will be called. But in most cases, it's just going to be like a stack allocated variable. And so whenever that stack frame pops, whenever that like scope is ended, this destructor will be called. So I'm not going to it would be easy to show you examples, but I don't want to take that time up. This is a simple C++ thing. I'm just introducing if you've never seen it before. And we're going to make it virtual. The reason for this is, like, what virtual means is it's somewhat similar to what abstract means in Java, where abstract means I'm saying this thing exists, but if you don't define it, you can't create an instance of this object. So it's like, it's almost like specifying a requirement for child classes to implement. In C++, it's a little different. You have to mark any function or constructor as virtual if you want to be able to overwrite it in child classes. But if you want to achieve the same effect as in Java, which you do in some cases, saying like this doesn't exist by default, but child classes have to implement it, you do equals 0 at the end, which is just, it's like arbitrary syntax. But what this says is this is virtual, so it can be overridden in child classes, but I'm setting it equal to 0, which means I'm not defining it at all in this base class. So child classes must implement their own version of that. So we're going to have a Voidbind function here. Like I was saying, this will just be like a generic thing that all of our classes need to bind them wherever they need to go for OpenGL to use them. And then we'll have the same one for virtual void unbind. Also going to be a pure virtual function. That's what these are called when you assign them to 0. And the reason this is virtual is, I think I already explained this, but there are a lot of different ways that our stuff is bound. Different methods, different syntax, which is the annoying one. So GLBind Vertex Array is used for vertex arrays. GLBind Buffer is used for buffers. You can see these are both different method names and they take different arguments. So we're just going to make it simple and define all of those in the proper child class rather than trying to make everything generic and do it all through here, which may be possible, but I haven't figured out a clean way to do it. And then lastly, we will have this get ID, even though I made fun of it earlier. So this is just for the outside world to access our ID thing here. And this is good for when other classes need to do something with this GL object. I can't explain it, but you'll see when we actually use it. Okay, so that's our GL object class. Now let's quickly move on to buffer, and we can see why we need to define this sort of default thing that doesn't actually give a real value to the ID. So I'll create a new header file here called buffer. It's going to be in our graphics namespace. I'm going to include it before I forget. Include buffer.h in our all file. So what buffer is it's going to be templated, and it's going to have some weird syntax that makes it abstract, as in the outside world can't instantiate one. And the reason we want that is it's just going to be sort of what GL object is for all of our other classes, how it stores this common data and has some common function declarations. Buffer is going to be that for our different types of buffers. So right now we have two types. We have the vertex buffer, which stores vertex data, and the index buffer, which stores indices into that vertex buffer. Later on, we'll see one called a uniform buffer, which is used with shaders. But because we have, I think we'll just have 3 different types. There are more, obviously, but because we have even 3, it's a lot nicer to have this sort of common base class that they can all run through, so you don't have to rewrite a bunch of code. So this is going to be a template, and it's going to take a GL enum as its template parameter, not a type. We're not interested in storing any kinds of generic types here. So we have class buffer, and this is how you do, in Java you do extends GL object, but in C++ you do this little colon, and then you have to specify an access modifier. We're going to use public for everything. If you want, you can research what the different ones are, but I think I've only ever used public. It's one of public, protected, or private, but we'll just use public. So in our class here, normally, as I said, you'd have your constructors in this public part. But because we don't want to be able to instantiate a buffer like this, we want to do it through one of the child classes, like a vertex buffer class or an index buffer class. We're going to use a trick, which is making our constructors protected, which, if you remember, prevents the outside world from accessing them. But it will allow our child classes to access them, which is exactly what we want, because we want those to be able to instantiate this, obviously, but we don't want to be able to create one ourselves. So we'll do that in a minute. But first, we need to actually create the bind and unbind methods, because in our GL object we specified those as pure virtual functions, so we need to actually define them here. And this override keyword here is similar to the I don't remember what it's called, a tag or something in Java where you do like @override above the thing, and you would do this for like toString or whatever if you're, or equals if you're overriding a definition from some base class. In C++, you do this with the this keyword. It's not necessary, but I like to put it on there just again because the compiler can catch it. Like if you spell it wrong or if you give it a different return type, like if I say float here, the compiler will be able to say, okay, well, I'm trying to look for the virtual definition of this float bind. All I see is Voidbind, so I'm going to yell at you. So I just like to put that on there because it can help out. So let's take a look at what we actually need to do for our buffers. So Vertex Array, we're not doing that yet. We're doing buffers. So vertex buffer and index buffer. And if you notice, they're bound with the same function, GL_bind buffer. The only difference is this first parameter they take. And that parameter is going to be our target, which is this template parameter of the buffer class. So we're going to say GL_bind buffer to target. And I've left it all caps. That might be like weird syntax. I'm not sure if that's common, but I tend to do that with my template arguments just because it makes it very clear what they are. So all we're doing here is saying, okay, target is going to be either GL array buffer for a vertex buffer or GL element array buffer for our index buffer. But whatever it is, we use the same function, put the target in there, and bind the ID. And then we'll do the exact same for the unbind, except we're going to put 0. So 0, depending on the implementation of OpenGL and also what kind of thing you're working with, 0 can or cannot be a valid identifier. It depends. So I don't know. This might not be like technically correct, but I'm pretty sure that at least when I've run this on my computer, I've never gotten any of these like GL_gen buffers or GL_gen vertex arrays. I don't think those have ever returned 0 as the identifier. They always start at 1. But just know that in certain implementations on certain systems, 0 can be like a valid thing. But I'm pretty sure for my stuff and the way we have this set up, 0 is like the null element. So it just means like don't use anything. But again, we won't be using that very often. So even if it's not 100% correct, it's not a huge deal. Okay, so now we're going to have this get count method. And this is just going to return the number of elements in this buffer. So if we look at our vertex buffer, or sorry, our vertex data here, this would return 5 times 4, so 20. And for our index buffer, it would return 6. Very simple, but also useful. Okay, so in our protected little area here, obviously we're going to need to store the count as mcount, and then we are going to write our constructors. So we'll have a single constructor that just takes a count and passes that count onto its own thing. I'm actually going to move that down to another line. And then, taking a look at our main file once again, we can see that our buffers are not only bound in the same way, but they're created in the same way with GL_gen buffers for both the VBO and the IBO. So we can do exactly that here. GL_gen buffers, size is going to be 1, and the pointer to our buffer, can anyone tell me what that should be? Sorry, I guess the pointer, yeah, the OpenGL ID of our buffer. Where should we store that? We're going to be putting it in ID. So now I will explain the reason for this default nothing constructor. So I'll go ahead and write this. So if I compile this, it'll go just fine. But if I take out this guy it also works. Shoot. But so yeah, it still compiles because this follows the same rules as the copy and move constructors. Like the compiler will generate a default one for you if you don't specify it. I'm not sure if you can delete a constructor, but either way, that was a bad example. The reason we're doing this is because our ID field has to be assigned to by one of these GL whatever functions, right? And it happens in different ways. Like I said, for the shaders, you assign the return value of those functions, but for these, we just pass a pointer. And so as the default constructor here, I've just said, like, don't give it anything, because later on, I'll assign to it in the actual method or in the actual code that runs in this constructor. So let's quickly talk about a slight difference between Java and C++. In C++, you have to create you have to call the constructor of your parent class. And in Java, this is done with super, the keyword super. C++ doesn't have that. So really what this should be, like, if I go here and say, okay, I don't want this default thing. I want you to give me the ID as part of my constructor. And then I'll just assign that and do nothing else. So if we do that now, because we've specified a constructor that takes an argument, this will work. It's because I'm not using it. I'll just do a small example here. You don't have to do this. I'm just proving that it won't compile. So if I have a buffer, I'll call it B. And that takes a count. I'll give it 10. Oh, shoot. This is another bad example because it's protected. Let me move that out real quick. Once again, you don't have to do this. Okay, now let's try. And compile. See what it gives us. Oh, I didn't give it a template thing. There we go. So we see the error is GL object, no appropriate default constructor available. So default constructor refers to either the constructor automatically generated by the compiler or a constructor with no arguments, which you can see I've explicitly specified here. And the reason this doesn't work is because we have to explicitly construct our parent. And so if I've said, this is my constructor, like I've created a constructor, the compiler will see that and it won't generate a default one. But I'm not actually calling that constructor. It requires a value. I'm not giving it a value. So what I'd have to do is say GL object and then some ID. And now it'll work. But as I've said, that doesn't make any sense because we're assigning to ID here anyways in the actual constructor. So that's why I've done it like this. Just specified this default here. And if you want, you could like assign to MID down here, just set 0 as the default value down here. I don't tend to do this. This is just like a syntax pattern I don't use for whatever reason. I try to do everything in the constructors because you just have to look in one place. So you could do this and then just not specify a constructor at all, and the compiler would generate one for you, and that's fine. But I like doing it here. But yeah, so I'll move all this back now. That was a bit of a messy example, but hopefully you get the point that if we have a constructor that takes an argument, you have to call that. And because that argument is never actually going to be used, that whatever random ID we assign, it's just going to be replaced by this. So I guess that's another thing I should say, is if you have a default constructor, because it takes no arguments, the compiler will insert that for you here. It'll do this. And you can do that explicitly and it'll work, but there's no need because it doesn't need to be passed anything. The compiler just does it for you. Okay, so that's our buffer constructor. We're going to do the exact same thing as we did with GL object. with our copy and move constructors. We're going to delete them. Once again, the reason for this is that we don't want to accidentally invoke the automatically generated copy and move constructors, because they won't do what we think in all likelihood. And that has cost me days of debugging in the past, is doing incorrect syntax. Like I think it's doing something different than it is doing. It calls one of those default things. It doesn't make any sense. It's incredibly difficult to trace when that happens. So just doing all of this, like this extra 2 lines up front in every class, will both give us peace of mind, and if we do end up messing something up, the compiler will yell at us. Okay, so I've written this destructor here, and I've also marked it virtual because remember our buffer class will be extended in a minute by a vertex buffer class and an index buffer class, and those we might want even further destructors. So I've marked this as virtual just so that we can overwrite it in those. Well, it's not overwrite. I'll explain that when we get there. But this is something that we actually didn't do in our main file, and we should have done, but it's a small example and it doesn't matter. I didn't want to bog it down with extra stuff, but it does exactly what it says it does. Whenever you create something in OpenGL, you should delete it when you're done with it. And this just does it in the destructor, which is nice, because it means that the user can just use this buffer class, and then whenever they are done with it, it'll take care of all the cleanup. They don't have to do anything else. So that'll just delete our buffer at the ID that we've passed it. Okay, now I'm going to write a templated function here called write. And it's going to take 2 parameters. One of them is the size, so the size in bytes of the array that we give it, and the other is this array, array of generic type of t, whatever that is. And all we're going to do is upload whatever's in data, size bytes of whatever's in data, to the GPU. So this is where we're going to use GL buffer data here, which is the most important part, other than binding. Because you can create something, but if you don't put data in it, then it's useless. So first things first, we're going to bind our buffer, whatever it is, vertex or index, just so that this next GL buffer data call will operate on this buffer. And then buffer data takes a target, which will be our template parameter for the buffer class, which is going to be either GL array buffer for vertex or element array buffer for index. Size, which we've taken in as an argument here. Data, which we've also taken in as an argument. And then usage. So usage is that GL static draw thing we've seen here. For now, we're just going to leave that, but eventually we'll probably change it. So once again, our target is a template parameter. We're given the size and data by the method, and then we'll just make it static draw. Okay, so this is all the base functionality of a buffer. And if we go back to our main, we can see this. The first step is to create one with GL gen buffers, which is done by our constructor. The second step is to bind it and then upload the data to it, which will be done by our write constructor here. Write method here. And then the third step, which we didn't do here, but you always should do, is to destroy it when you're done. So whenever our buffer goes out of scope or we delete the pointer to it, OpenGL will free up that spot. Okay, now we're going to write the specializations of this. So we'll have Vertex Array, and then we'll do Index Array in a minute, but let's just start with this one. So first things first, as always, I'm going to just copy that line and include it in my main thing. Oh, I named it incorrectly. That is vertex buffer. We'll do vertex array after that. But yeah, just include it so we can use everything, and then also our main file gets it. So same namespace. GFX, class vertex buffer, it extends a public buffer, and the target, does anyone know what the target will be for this one? Look at your main file and see if you can tell.
The bind buffer?
Yes, so it's used by bind buffer. Target, this whatever variable we put here is used by bind buffer, but what should it be for a vertex buffer specifically?
Is it GL array buffer?
Yes, GL array buffer. Very good. So that will be our template parameter there. All right, and then everything in here is just going to be public. We've done most of the work that we need to do in buffer already, so we don't need to store any sort of state in here itself. So first is the constructor, which will take a count, which is necessary for our buffer because our buffer, the only buffer constructor, takes a count. So we need to give that to vertex buffer as well to pass down. And then it's going to take a pointer to some data. So this might seem like weird syntax. I'll explain it in just a minute. And of course, we have to create our parent. I think you have to specify this template parameter here as well, just to tell the compiler that, like, hey, I'm calling this specific specialization of the template class buffer, where this is the argument. You might not have to, and it probably depends on the compiler, but I always like to do that just in case. So we're just passing that count variable down. And then now that this is run, if we take a look at that constructor real quick, we can see that this generates the buffer and it assigns to the ID. So just for debugging purposes, I like to print to the console that we've done that. So we can do create VB, give it an unsigned int, which is our ID. So in this way, we can keep track of when stuff is created, when it's destroyed, and what numbers it gets, basically, what internal IDs it gets. So once we've done that, we'll go ahead and bind our buffer. Actually, that's not necessary at all, because our write function will bind for us. So we can just do write, and this takes a size and a pointer to data. So this is that distinction between size and count. Size is number of bytes. Count is number of elements. So we have the count, and we know the data type is float. So we'll just do count times the size of a float is the number of bytes that we want to write. And then we'll give data as our pointer. Okay. So this syntax right here, it's the same thing as I was talking about with references, where you read them right to left. So normally, like you would see, this is more common, where you have a pointer to a const float. To it's like a floats that you can't modify. But here we have a const pointer to const floats, which means that not only can the data itself not be modified, you can't change this pointer. And this is not necessary, like it's not going to affect anything we write, but it is technically correct, just because it's like the most const correct way, because we're not modifying the pointer. We have no need to do that, so might as well tell the compiler that we're not doing it. And in fact, we could come down here as well in our buffer write method and define that similarly as a const pointer to const t's, whatever t is. Okay. Then, of course, I'm going to do the boilerplate of deleting the copy and move constructors. Which is good. And now in our destructor, we don't really need this, but again, I just like to log when stuff is created and deleted. MID, and that is not what I wanted to write. I want to say delete vertex buffer and give the ID. So it's important to note that, and this is going back to my initial explanation of the virtual keyword. So this syntax, this sort of pure virtual function where you do the =0 at the end, is as far as I know, like exactly equivalent to Java's abstract keyword. The regular virtual, though, obviously it means you can give a definition for this in this class, and then also sort of give another definition for it in a child class. But the child class definition does not override this. They're actually separate functions, and they're called in a specific order. So in the constructor, this order is from parent to child. In the destructor, it's from child to parent. So I'm not going to go into this too much. Again, it's a C++ thing that you can look into if you don't know it already. But this makes sense because here we're creating our parent buffer before we run any of our constructor code. And then in buffer itself, remember there's this sort of compiler given default initialization here that happens before this code runs. So we have the ultimate parent GL object, and then the buffer will run its code. And then once that is done, the parent of Vertex buffer is done, Vertex buffer will run its constructor code. And in destructors, it's the other way around. So this will run, and then our buffer destructor will run, and then our GL object destructor will run, which is just nothing. And this might be important later on, but I think most of all it can just be confusing because you could say, oh, well, okay, so you've done this, but then you're not actually deleting it. Just know that this is running, and then immediately after that, the buffer is actually getting deleted by the buffer deconstructor. Okay, so that's our Vertex buffer. Very simple, like we've done most of the work in the buffer class itself, so we just needed to use all of those functions here. Next, we're going to do the Vertex Array. We could do index buffer next, but it's mostly the same as Vertex buffer, so I'd like to show something a bit more interesting here. So Vertex Array. Go ahead and include this in my all.h. Put it in the graphics namespace. And then because this is a vertex array and it's not a type of buffer, it's just going to inherit from GL object, not from buffer. Okay, so what a vertex array does, if we take a look at our code, and I said this several times last time because it's important, is you create a vertex array, and then it's sort of, if you create a vertex buffer, or if you have bound a vertex buffer while a vertex array is bound, any of these enable vertex attrib arrays that you call, which remember operate on the bound vertex array, those will, like the vertex array will associate those with the buffer. That's confusing, but essentially it just removes a step from what we have to do. Where normally we would have to store metadata about the vertex buffer, and we would have to sort of map that ourselves and say, okay, this vertex buffer pointer maps to this metadata. But vertex array just does that for us. And it's sort of weird syntax, and it's confusing just because it's all this binding and like stuff happening behind the scenes, but just know that that's what it's doing. So what we're going to need here is in our constructor, which will be public. So we need to both create a vertex buffer, but then also describe that. So how do we create a vertex buffer? Well, let's just use the class we just wrote, vertex buffer, and I'll call this im_buffer. Now, we have this other vertex, this other variable im vertex size, and I'll just leave that there and then we'll get into it. So we have our constructor, and then of course we have all the stuff we have to override from GL object, which is bind, unbind. But yeah, let's write the constructors first because that's the interesting part. So I'll take uint count and const pointer to const floats vertices, which, if you remember, is exactly what the vertex buffer constructor requires. So let's see if we can tell why this is yelling at me. Yep, exactly. No default constructor exists for class vertex buffer because it needs 2 parameters and we haven't given it any. So let's do that. And this is exactly the same syntax, I guess, as as like what did I call it? You have to create your parent. It's like sort of the same thing, where whatever you put in here is just going to be passed to the constructor of this variable. The only difference is that instead of saying, as I accidentally did here, the name of it, like the name of the type, you do the name of the variable. And then whatever you give it here will be passed to the vertex buffer constructor. So we have count and vertices, which is good. And then I'm going to do something a little weird for this mVertex size thing. I'm not going to explain this. This is just something cool you can look into if you want. But it's a standard method that operates on a list, or I guess a range, and applies this function to it. So I don't actually have that because I need to include it. So in my PCH, let's see if I can remember which file this is in. It's probably in, well, actually, why don't we just include a bunch of stuff while we're here? So we'll need vector eventually. We'll need unordered map. What else do we need? Standard IO is good to have. We'll need file streams, so I'll do IO stream and F stream. What else are we going to need? I think this standard reduce thing is an algorithm, maybe, or it might be in numeric. I don't know, but just a bunch of includes here. Remember, our PCH is the pre-compiled header. So this is something where we put all the code, we include all the code that's not going to change that often. And then Visual Studio will say, okay, I know that this hasn't changed, so I won't recompile those. This thing has changed, so I will recompile it. But the rest of it I'm just going to skip out on. So it saves time during compilation, which adds up. But generally, it's just a place where we're going to put stuff that is useful to the rest of our code. And the sort of generic includes vector, unordered map, standard IO files, all that is good to have here just because that's not going to change. It's library code. We can't change it. And it's useful to have just in various places. So you can see there I've included standard reduce. That's probably an algorithm. It might be a numeric, or maybe it's standard plus that's a numeric, but either way. So what this list thing is that I haven't given is another sort of weird thing that I will explain, called an initializer list. And this is a really cool class, or struct, maybe. Oh no, it's a class initializer list. I'm not sure how it's implemented. I would love to see that. You could probably see it on CPP reference if you Google it. But it's really cool. It allows us to, I'll just do a quick example up here. If I do like a standard initializer list of floats called list, we can use this sort of brace initialization syntax that you use for structs. And it'll take this and sort of generate a temporary type. Like the compiler will generate a type for this structure and store it for you. So you don't have to define a struct saying, okay, this has 3 elements or however many elements. And why that's useful, I'll just delete that, is in our vertex array, what we're going to use this list for is this, the description part of the vertex array. So we have this count, which is the number of elements in our vertex list. We have this vertex list, which is obviously the data we need to send to the buffer. So that's all good. But in order to describe it, we need to sort of separate each. We need to, as we've done here, we need to separate it into groups. Right now we have 2 groups. We have this 0th group, which is 2 floats, the x and y, and this 1 group, which is RGB. And so the way we're going to do that is by passing an initializer list where each element in the initializer list is the number of elements in a group. So in this case, because we have 2 elements in this group and 3 elements in this group, our initializer list would look like 2, 3. And this, like, we're just going to take it on good faith that the user knows how many elements are actually in each vertex. What we could do is like include a separate variable that the user has to specify to do that, to do a little bit more automatic error checking, but we're not going to do that. We're just going to keep it clean and simple. Just take an initializer list, and then the vertex size, which we're assigning here, which is the number of elements in each vertex, is going to be the sum of all the elements in this list. That's what this does. Again, I'm not going to go into the syntax, but just know that this vertex size equals the sum of all the elements in list. Okay. So now in our constructor, obviously we have to create a vertex array with glgen vertex arrays, just one. And then of course I'm going to print, just let us know that we've created one, give the ID. Now, the next step is to describe stuff, but as I sort of explained here, in order for the vertex array to correctly associate the description with the buffer, everything has to be bound properly. So first of all, we're just going to bind our vertex array. Then we're going to bind our buffer. And then we're going to describe it. And this is exactly what we've done here in our main file. We've created a vertex array. We've bound that vertex array. And then once we've bound our vertex array, we bind our vertex buffer, and then we describe. So that's what this is. Bind vertex array, bind vertex buffer, and then describe. So I'm going to define this variable outside here, stride, which is vertex size times size of float. Oh, size of float. And that's just the number of bytes in each vertex. And then I'm going to do this a little ugly. You could probably refactor this and make it prettier, but this works for me. So offset is going to be the byte offset of the current group that we're specifying. If we look at our main, that is this last parameter here, which annoyingly you have to pass as a pointer. So that's just the thing that's like, the size here should be the size of the sum of all groups coming before it. So for the first one, it's 0, but for the second one, it's 2, which is the number of elements in the first group times the size of the float. So that's what offset is. And then I is just the current group that we're on. And the reason I'm not doing this in a traditional for loop where I would just be the counter variable is so I can go through like the list with this for each syntax. Because I think the reason I've done this is there's no actual way, you can't do like list at I. That doesn't exist. No operator matches these operands. The compiler won't generate that for you. But we can go through it with this like range-based for loop here. Okay, so the first step is to enable the attrib array at the index. Our index is I, once again. And then we set the data for that attrib array with gl vertex attrib pointer. The index is I. The size is going to be in, because remember here, size, this really should be count. This is the number of elements in the current vertex group. And remember again that each element in our initializer list here specifies that. So that's the number of elements in the current group in. We're just going to say they're all non-normalized floats. You could make that generic if you wanted. I don't think I've ever like passed data to a buffer that's not floats though, so there's not really a reason to. Well, I'm sure there are reasons to, but we won't be doing it. Then stride, which is going to be the same for all of it. So really we should mark this as const uint stride, because that's not going to change, which is the number of bytes in each vertex. And then of course we have to cast to a const void pointer the size of all groups coming before it. So that's where our offset variable is going to come in. We'll do offset times size of float. And then once we're done processing this or describing this group, we will add the number of elements in that group to offset. And then we'll just do I++ at the bottom. Okay, so that's our constructor. We do have a bit more to do here. I'm just going to sort of leave this for you to like, because I'm sure you're not like 100% getting everything I'm saying because you're also having to type. I'm going to leave you to sort of take this and make the mental link between that loop and what we're doing in here in the main file. So don't delete that main file because this is exactly the same stuff. I'm just doing it in a loop to make it generic so that it can support any type of vertex array, any description you want. So we're going to do our copy and move constructors. Boring, boring. Delete both of those. And then in our destructor, say I'm deleting this vertex array. And then we actually delete it with GL delete vertex arrays. Like that. So I'm not sure if this GL delete vertex arrays, if that can actually modify the value stored in ID. My suspicion is no, that wouldn't really make any sense, but just in case I print it before, just so that if we delete it and it does modify it, we don't print out delete VA and then some garbage number that doesn't mean anything. Okay, so now we'll do the overrides here for GL object. The bind function we use for vertex array is GL bind vertex array, MID. And then for unbinding, we'll just give it 0. Okay, now I'm going to do one last method here, get vertex count. Oh, excuse me. Big hiccup. So here, this is if we want to get the number of vertices in our vertex buffer. Now, this could be done, and there's a legitimate argument that could be made that it would make more sense to put this in the vertex buffer itself. And you could do that. The problem, though, is that vertex buffer is just a buffer, and all buffer stores is count, which is the number of elements. It doesn't know anything about the size of each vertex or the number of vertices. But our vertex array does, because our vertex array has this imVertex size variable, which is the number of elements per vertex. So I just did it here, but it might be cleaner to do it somewhere else. I'm not sure. So we do imbuffer.getCount, which is the number of elements total divided by the number of elements in each vertex. So that'll give us the number of vertices. Okay, and that is our vertex array class. So it's pretty simple. The real complexity is here in this loop, but again, I'll leave that up to you to decipher. Okay, next we're going to do our index buffer. I'll include that in all.h. Index buffer. And this is going to be a buffer. Can someone tell me what the target for this one is? For our vertex buffer, it was GL array buffer, but what will it be for the index buffers? Check the main file. GL element array buffer is the slot that we bound our index buffer to, because remember, buffers are all the same thing. The only difference is like abstractly what they represent, which only we know, and then based on what they represent, where you put them. So vertex arrays go to the array buffer, and index buffers go to the element array buffer. So that'll be our template parameter here. GL element array buffer. And then this is going to be not quite as simple as the vertex buffer. It's going to look a bit weird, but I'll just go ahead and write it. So the constructor for this is going to take a vertex array. And the reason for this is that we're only ever going to use vertex buffers and index buffers together. And remember, a vertex array contains a vertex buffer. So I don't really see a need to define a constructor that doesn't take in a vertex array and generate index data specifically for that array. But you could if you wanted. I don't know, but we're not going to be using that. So first thing, of course, is to instantiate or create our parent. And we need to tell it the count here. So let's see if we can look at our main file and establish some relationship between the number of vertices in a vertex buffer, which we can get easily with this getVertexCount method that we just wrote, and the number of indices required to draw a square from that. Because all we're doing, or not square, but a quad, a rectangle, all we're doing is drawing rectangular textures. So we have vertices here. We have bottom left, bottom right, top left. That's 4. But to create that as a quad, we need 6 indices because there are 2 triangles required to create a quad, and each triangle has 3 vertices. So that'll be our little formula here, is va.getVertexCount times 6 over 4. For every 4 vertices, we generate 6 indices. I'll do my little printf here, create index buffer ID, and then we'll go ahead and bind it. Actually, we don't need to bind it once again because write does that for us. So now we have to generate the data itself. Now, because the number of indices we need to generate is given by this getVertexCount method times 6 over 4, it is not a compile time constant because getVertexCount cannot be a compile time constant because it's like, I think you get the idea. It's just, it has to be resolved at runtime. And what that means is that we can't create an array on the stack. We have to create it on the heap. And I've already showed this, but you do that with this this new syntax, just like Java. But the important thing to remember is that if you create an array on the heap like this, you have to delete it yourself. Otherwise, there's no garbage collection in C++, so we won't do that. So the syntax for deleting a pointer in C++, a single point. So I could do like uint a equals new uint, like that. Just create a single one. To delete that, you would do delete a. But because we've said this is an array, you have to do this delete with the little square brackets at the end, which is kind of weird, but whatever. That's just how you have to do it. Okay, so we have the space for our data now. Now let's populate it. So we have count indices that we need to generate. So we'll just do a loop. Now, let's see if we can recognize a pattern, because we want to generalize this again so that the user doesn't have to specify any of this at all. So we want to automate the index generation process. And we can do that again just by looking at our vertex data and our index data. So for one quad, we have this pattern. Once again, assuming the convention of counterclockwise from the bottom left. Defined, like that's how the vertex data is defined. And that's fine. You know, like we're writing this library. It's perfectly reasonable of us to impose that restriction on the user. So yeah, we'll just assume that the vertex data they've given will require that that is defined in this order of counterclockwise from the bottom left. And then using that, we can, where to go? We could just use this pattern as sort of an offset. So in my index buffer here, I'll come down and create a compile time constant static array of uints called offsets. And they'll be exactly what that array in our main file takes or contains. So compile time constant static, so it doesn't belong to any one instance. It's a member of the class itself. S underscore is what I use for static variables, much like m underscore for member variables. And then we can just initialize it with this brace initialization list here. So if we just have one quad that we're trying to draw, this works just fine. But if we have two different quads, then we need to add some value to this. And I guess a good way to show this would be if I take this data in vertices and just copy it. Like, imagine this is something different, but for the sake of example, these are two separate quads. They are different data, and we want to draw both of them. So this index array here does just fine drawing this one quad because it uses indices 0, 1, 2, and 3, which is good because that's our first 4 elements here. But this next quad, the index starts at 4, 5, 6, 7. And if we want to draw that in the exact same way, then we would go from 0, 1, 2, 0, 2, 3 to 4, 5, 6, 4, 6, 7. So that's all we're going to do here, is we're going to any position in the array, we're going to assign the value at f offsets of I mod 6. I mod 6 will give you the, because there are 6 indices for each vertex, or sorry, 6 indices for each group of 4 vertices, will give you like the index that you're currently working on. And again, this is going to be something that you're probably going to have to decipher yourself somewhat. And then we'll add this I over 6, which gives you the current quad that you're generating indices for, times 4, because there are 4 vertices in each quad, so you want to add whichever number of quads you have already done times 4 to get the current, like the bottom left, the index for the bottom left corner of the current quad. That's what this I over 6 times 4 is, and then you add the offset. Yeah, so that's a very clean way to do it. It's sort of like confusing though, but again, I'm sure you can figure it out. So now that we have our data, we're actually going to write it. So the size is going to be the number times the size of a uint, because that's our data type in this case. And then our data is just going to be temp. And then once we've done this write call, it's uploaded to the GPU. We don't need this pointer on the heap anymore, so we can go ahead and delete that. And that's the end of our constructor. Then, of course, we're going to do our copy and move constructors. Just delete those. Like that. And then in our destructor, just print that we have deleted it. All right. So that's a very short class, fairly simple, but again, the complexity is in the loop here, just like the vertex array. Okay, so I think that's all we have time to like write our classes today. Next time, the very first thing we'll do next time is combine a vertex array and an index buffer into an object, just called a render object, which is just something that's going to be drawn all at once. It uses a single vertex buffer, a single index buffer, and just draws it. So that'll make it a bit cleaner. But what we have right now, we can actually improve our code quite a bit here. So I'll just get rid of that dumb example I did. So we have vertex array, vertex buffer, vertices. We need to keep this because we'll need to send it to our object. All this binding stuff happens automatically now. All this description stuff happens automatically. Index stuff happens automatically. It's just that the shaders are not done. We don't have classes for those yet. So I'm going to go ahead and take steps 1 through 3 and just comment those out. If you're in Visual Studio, you do that by highlighting it and then pressing Control, K, and C. It's a nifty shortcut. Okay, so now we're going to do the exact same thing we did here. Oh, I'll take our vertex data as well, because we still need to upload something. And then uncomment that with Control K and U. Okay, so we're going to create a vertex array and an index buffer with GFX vertex array. I'll call it VA. And what does this take? It's not showing me. Vertex array needs a count and the vertices themselves, and then the list telling us what the groups are. So the count will be math rlen on vertices, the number of elements in there. Then we need the vertex data, and then we can just pass the standard initializer list using this cool curly braces syntax, and we have two groups. The first is our x and y, which is 2 elements. The second is RGB, which is 3 elements, just like that. And then now that we have our vertex array, we can create an index buffer. I'll call that IBO, and the constructor for that takes a vertex array. So we'll just pass it that, and there we go. So now, fingers crossed, if I scroll down here to my game loop, where all of this is being drawn, we can go ahead, I'll just comment all of that out. We will do va.bind, bind our vertex array, then we'll do ibo.bind, bind our index buffer, and the GL draw elements, same mode, GL triangles. Instead of rlen on indices, we can do ibo.getCount, which, remember, if we look at buffer, count is just passed through the constructor. It is the number of elements in that buffer, period, which is what we want here. Just the number of indices to go through and generate for. Same type, it's all unsigned ints, and then null pointer because we have it bound. Okay, so let's see if this runs. Hey, awesome. We get exactly the same thing, which is uneventful. But you can see now that we have this nice little output here, sort of confirming that this stuff is not, at least again on my system, whatever implementation of OpenGL my graphics card is using, they don't start at 0, the indices. So vertex buffer, the first one generated as 1, vertex array, the first one generated as 1, index buffer is 2, which is cool, because you can see there that vertex buffers and index buffers truly are the exact same thing. OpenGL said, okay, you've already created a buffer 1, I'll give you a new buffer 2, and we say, okay, I'll take that. That's an index buffer, but OpenGL doesn't know that. Okay, so we have the exact same thing here. If we close this, we should get that output, just in reverse order. Delete the index buffer, delete vertex array, delete vertex buffer. And yeah, there we go. So we've taken, we still have all this shader messiness, just ignore that for now. But we've taken, ooh, what is this? Probably about 50 lines of code here for our vertex and index buffers and description stuff. and turned it into 10, which is awesome, and it's very clean. Vertex Array automatically creates that vertex buffer for us. It automatically describes it with this neat syntax here, where we just tell it how many are in each group. And then the index buffer, all we need to do is pass it this vertex array, and it'll look at however many elements are in that vertex array and dynamically generate however many indices it needs in the correct order. It does all that for us. And then instead of doing these ugly GL whatever functions, GL bind vertex array, bind buffer to the correct target, we just call va.bind, ibo.bind, handles all that stuff for us. And the GL elements, we do still have to call this, but we will get to a point next time where even this call will be done within a separate object. And I guess I maybe haven't made that clear, but that's sort of the goal with our abstracting all of this out into a graphics library, is that the users of our graphics library shouldn't have to write a single line of OpenGL code themselves. None of this GL whatever functions, none of that the user should have to write. All of it should be encapsulated within these classes and simplified through this interface of functions, of methods on those objects. So here we have bind, obviously for the vertex array and buffer, which sort of removes the complexity there. GL draw elements, we're going to have a class called renderer, which just takes something in, draws it using this function. So this will be replaced eventually with like render.draw, whatever. And then this swap buffers, poll events, and clear stuff will also be handled in the renderer. We'll have like render.clear. And then after we've drawn everything, we'll have, for this third step, render.render, that kind of thing. So all this GLFW, GL, none of that will be in our main file, which is great because it's very ugly, very confusing, and I mean, that's the point of writing a library, is to remove, to provide a layer of abstraction on top of OpenGL so that we can write that code once and then just use our objects within our files, which is a lot easier. Okay, so I'll just delete all that nonsense real quickly. Once again, I'll show the output. Oh, I got this weird error thing again. So this can be scary. This is what I was talking about. When you get into doing OpenGL stuff and you see this, like your heart sinks. All you have to do, close that, close the console, and then there you go. I'm not sure what causes that. But yeah, there we go. So next time we're going to combine vertex array and index buffer into a single object called a render object, just for convenience. Because once again, in our case, those are always going to be used together. In some cases, they won't be, though, so that's why I separated the vertex array and index buffer out into separate classes in the first place. But just for our specific use, we can go ahead and combine them into one thing. Then once we've done the render object, we'll write the renderer, which, as I said, will take the place of all this GL stuff in the game loop itself. And then after that, we will do shaders. Shaders are probably the most complex thing, like code-wise, that we'll be writing, or as part of this abstraction that we'll be writing, just because there's a lot going on. But the result will be really cool. We'll be able to have an external file with this source code in it, and give that to a shader object, and the shader will read through the file, determine what's vertex code, what's fragment code, separate it out, compile them, do all of this ugly nonsense together, report errors to us if there are any, all of that. So it's definitely a bigger, it's a lot bigger than the stuff we did today, but I think we'll have time to get through it tomorrow, and it's definitely worth it, because having to hard code this shader source code as strings is just such a pain. But yeah, so that's what you should look forward to next time. More cleanup via the renderer, just making this VA and IBO stuff a bit more compact, and then getting rid of all this ugly, 50 lines of shader nonsense. So yeah, thanks for showing up, and I will see you on Saturday at 4.